Hello guys, today's video is a past paper walkthrough for the exam board Oxford AQA International A-Level Chemistry. This is for paper 5. I know many of you guys have this paper coming up for exams, so this is just mainly a walkthrough on all the questions. This is a Specimen 2018 paper, so it's a 1 hour 25-minute paper. It's just a sample of this paper of paper 5. If you guys have enjoyed the video, please do like, share, and subscribe. Channel really helps a lot. And yeah, let's start with the video. All right, so the materials that you need for this paper are a pencil, ruler, calculator, and data booklet. By the way, the formula booklet will be given to you in the exam. It's not a formula booklet. It's more of the insert sheet. It's going to look like this. This is how the insert sheet's going to look like. It's more of a periodic table of elements. So when you're doing chemistry, you'll have 2 pages. 2 pages of the periodic table of elements. Okay, so it looks like this is the periodic table of elements. You'll have that piece of data, table A, table B, table C tables. You'll have 3 tables on the chemistry data sheet. So let's move on to that past paper. So here, instructions: use black ink. By the way, this is really important that you bring a black ink pen to the exam. Okay, use black ink. Okay, show all your working. The maximum mark for this paper is 60 marks. Okay, so yeah, let's start with the first question. So the first question is, when water that reacts with soap, okay, to form that is called hard water. The presence of dissolved calcium or magnesium ions. The sample of water can be determined by titrating the water with a solution containing the ligand EDTA4-. EDTA4- reacts in 1:1 ratio, forming a very stable complexes with these metal ions. Write an equation for the reaction of EDTA with aqueous calcium ions, CaH2O6 2+. So this is more of a ligand substitution reaction, so do remember that the keyword they're giving you is ligand here. So what you're going to do is you're going to it's going to be Ca. We're going to write down the calcium ion, aqueous calcium ion first. So it's going to be, let me just erase that. It's going to be Ca H2O6 2+ plus EDTA4- plus the reaction of that, and then a ligand substitution. The H2Os are going to get replaced. The 6 H2Os are going to get replaced. So in this case, it's going to become Ca EDTA brackets 2- plus 6 H2O. Okay, this is going to be your answer for about 1 mark. Let's just resize this. So what's happened here is that you've reacted the calcium aqueous calcium ions, and you've reacted it with EDTA ligand. And what happened is that a ligand substitution happened, releasing out 6 water molecules. Okay, let's move on to the next question. A solution containing a known concentration of EDTA4- ions can be prepared using the hydrated disodium salt. RFM is equivalent to 372.4. Calculate the mass of the hydrated disodium salt required to prepare 250 centimeter cube of 0.0200 mole per dm cubed solution. outline the procedure for the preparation of this solution. It's for 7 marks. So what you're going to do is, first of all, we know some of the formulas for this. We're given the concentration and we're given the volume. So what we can do is we can calculate the amount of, or the moles of the solid in this case. By the way, RFM, I'm assuming it's relative formula mass of the hydrated disodium salt. So using the formulas over here, we have this formulas here of the, we're gonna take this out and we're gonna paste it right here. So okay, so we have this triangle showing us how the moles, mass, and MR are connected, and we have the formula for concentration, which is equivalent to moles by volume. So first of all, we have to calculate the moles of the solid. So the moles of the solid in this case would be the concentration multiplied by the volume, which is going to be changed to dm cubed. So what we're going to do is we're going to write these steps here. We know that the volume of the hydrated, actually the volume of the solution is 250 centimeter cubed. We have to convert this volume into decimeter cubed. So what we're going to do is 250 cm cubed divided by 1000 centimeter cubed. We're gonna first do that. We're gonna convert these values. Okay, so you get 0.25 dm cubed. Okay, 0.25 dm cubed, and we do know that moles is equivalent to concentration times volume. So that means the moles of the solid, the moles of solid is going to be equivalent to the concentration 0.0200 mole per dm cubed multiplied by 0.25 dm cubed. Okay, so now the moles of the solid is given. What we have done is we have multiplied the concentration of the solution and we have multiplied it by the volume of that solution, which is converted to dm cubed. So that would give it as 5 times 10 raised to the power of -3 moles. This is the moles of the solid. Then now what we're going to do is we have to find out what's the mass of the solid that is required. Since we're given that the relative formula mass of the hydrated disodium salt is 372.4, what we're going to do is we're going to use this MR and we're going to multiply it by the number of moles of the solid to get the mass of the solid required. So I'm just going to show you that step here, is that the mass of the solid required is going to be the number of moles, 5 times 10 raised to the power of -3 moles, okay, multiplied it by the MR, which is 372.4. We have taken this from the question itself, so we're just going to multiply them together. You're going to get it as a value of 1.862 grams, okay? Now, they had asked us to outline the steps for the preparation of this solution. So what I'm going to do is we're going to write that we're going to weigh the solid in a weighing boat. So that's going to be your first mark. You're going to weigh this 1.862 grams of solid in the weighing boat. Then you're going to add some water and stir to dissolve it. So this is really crucial that you add the water and you stir it so that the whole reaction mixture is completed and it's all reacted together. So you're going to add the water. You're going to add the water and stir to dissolve. Okay. Then you're going to transfer the washings. You're going to transfer the washings. Sorry guys, you're going to transfer with the washings. That's a better way of saying it. You're going to transfer with the washings. You're going to transfer with the washings to a 250 centimeter cubed volumetric flask. Okay? You're going to transfer all that washings to that. So these are some of the steps. These are 3 points. The first 2 points initially were calculation points, so you can score easily 2 marks for that. The other 3 points are to score 3 marks, where we're weighing the solid, and then we're adding water stirred, and then we're transferring it into all these washings to a 250 centimeter cube volumetric flask. Then what we're going to do is we're going to top up the you can top up to the graduation mark. You can top up to the graduation mark with distilled water. This is like I'm assuming this is a bit of pure water you can be using with distilled water. Okay, then what you can do is you can invert to mix. Invert to mix. So invert to mix is you can just invert it and then indirectly just mix this up together. So those are your 7 marks that you can write for exam. These are some of the points for the preparation of this solution. All right, let's move on to the next question. Okay, so the next question is a 25 centimeter cube sample of water is reacted with 5.55 centimeter cube of a 0.0200 mole per dm cube solution of EDTA4- ions. You're going to calculate the concentration in in gram per dm cubed of the calcium ions that are present in the water. So how we're going to do this is, again, we're just going to insert the formulas. What we know this formula, this triangle over here, and we know that concentration is equal to mole by volume. So what you're going to do first is you're going to calculate the number of moles of EDTA. Look at the values that are given to you. You're given the concentration and you're given the volume, so you're going to do the same steps. You're going to do concentration times the volume to give you the number of moles of EDTA4- ions. So first of all, the first step is to convert the volume of the solution. So we have to convert this to dm cubed to solve this, because you have to convert the values. So in this case, the volume, which is 5.55 centimeter cubed, we're going to apply the same steps. We're just going to put this formula here so it's more easier for you guys to see it. Yep. So show an arrow, 5.55 centimeter cube. Show all the steps in working out. Okay, divided by 1,000 centimeter cube. Okay, this should give you in the calculator as 5.55 times 10 raised to the power of -3 dm cubed. Okay, this is the volume. So that means the number of moles, we can just write it here, number of moles of EDTA4-. By the way, the N just means number of moles of EDTA, okay? So number of moles of EDTA is going to be the concentration, which is 0.0200 mole per dm cubed. Mole per dm cubed, and you're going to multiply this by the volume, which is 5.55 times 10 raised to the power of -3 dm cubed. You're going to get 0.0200. You're going to get it as 1.11 times 10 raised to the power of -4 moles. Okay, so this is the number of moles of EDTA. Now you need to know the number of moles of calcium ions. Remember, this is a 1-to-1 ratio. How do you know this? Is because they have given it to you from the start. EDTA reacts in a 1-to-1 ratio. If you look closely, it's a 1-to-1 ratio. So we know that the number of moles of calcium is of calcium 2+ ions are also going to be 1.11 times 10 raised to the power of -4 moles. So now we know the number of moles of calcium ions. Now we can calculate the concentration of calcium moles. So what we're going to do is you're going to resize. We're just going to resize this so that we can see all the steps and working. Okay. So now we're going to calculate the concentration of calcium ions. We're going to do it the moles divided by the volume. So now the volume in this case of the calcium ions are 25.0 centimeter cubed. You're going to do 25 centimeter cubed divided by 1,000 centimeter cubed to get it in terms of dm cubed. Really critical step that you guys do, 0.025 dm cubed. Then you're going to calculate now. I'm just going to resize this again. We need more space. Okay, we're just going to resize it. Hopefully this is clear enough. Yep. Okay. Now we're going to calculate the number of moles. The concentration of the calcium ions. Concentration of calcium 2+ ions is going to be the number of moles, which you have found is 1.11 times 10 raised to the power -4 moles, and you're going to divide this by the volume, which you just found, 0.025 dm cubed. Okay, 1.1 times 10 raised to the power -4. You're going to divide it by 0.025, which you're going to get it as 4.4 times 10 raised to the power -3. Mole per dm cubed. These are the units of concentration that you're going to use. 4.4 mole per dm cubed. Then from here, what we have to do is we have to convert this value into grams per dm cubed. Now the only way to do this is by us multiplying by the MR of calcium. How do we find out the MR of calcium, of Ca? We have to go to the, again, remember, you're given the periodic table of elements, the data sheet. You're going to go here and look at calcium. You can see that calcium over here has the relative formula mass of 40.1. So you're going to identify it from there, and it's going to be 40.1. So what we're going to do is, in order to convert the mole per dm cubed into grams per dm cubed, you're going to multiply it by 40.1. So we're going to write it here. I'm just going to resize this even more. Actually, I'm just going to put the formulas here. Okay, hopefully you guys have written down the formulas. So we have more space to write. They should have given more space a bit. Okay, so now we're going to calculate the concentration in grams. Concentrations in grams per dm cubed, which is going to be 4.4 times 10 raised to the power -3 mole per dm cubed. The reason why I'm showing all the steps is because this is really necessary that you show all the steps, even when it's a 3 marker. There are instances where it's fine, like if you show like few of the steps, but if you want to score those full points, it's more better to write all the points and all the working out that you're showing that you know how to solve this type of questions. So you're going to multiply the concentration with the MR 40.1 to get this in terms of grams per dm cubed, which is going to become 0.176 grams. Okay. Yep. This totally makes sense. I'm just going to check again some of the calculations. 0.025. Sorry guys, this is actually, when we divide this, it becomes 4.44. I just put this in my calculator now to just check. So it's 4.44. Remember, these make a huge difference when you put even one number here. So it's going to become 4.44 times 10 raised to the power -3 times 40.1, which is going to make it 0.1780 grams. So it's going to become 0.178 grams. Okay, grams per dm cubed. Remember, very important. grams per dm cube. Okay, just put all those units there. Okay. Yeah, this is your working out for about 3 marks. Let's move on to the next question. Now, the next question is talking about the maximum total error for the burette is plus or minus 0.15 centimeter cubed. This error takes into account multiple measurements, estimate the maximum percentage error, and using the burette in the titration. So what you're going to do is, what values you do have is that the maximum total error in the burette is 0.15, and we're going to divide this by the volume of the solution, in this case, because the titration you're involving the solution. So you're going to do it, and we're going to multiply this by 100%. So we're going to take this value over here, put it in the denominator, and we're going to take this value, put it in the numerator, and we're going to multiply it by 100%. So it's going to become 0. On top of that, they asked us to estimate the maximum percentage uncertainty. So 0.15 divided by 5.55 times 100. Now if we plug this into our calculators, we're going to get 2.7. The value is going to become 2.7%. Okay, if you round it off, it's actually 2.702. But if you round it off to two significant figures at least, it's roughly 2.7%. So just one way that the percentage error in the burette could be reduced. So this is one of the methods that you can use, is that we're just going to write the full point here, is that you're going to use a more dilute solution, okay, of that ligand, ADTA 4-. Okay, there are alternative ways, or if you check their marking schemes, these are some of the other points as well. You can use a dilute. They apparently write this as well. You can dilute the solution. You can dilute the solution of EDTA 4-. This is another point that they mention. Or you can also mention that you can use a larger than 25 centimeter cubed volume of water. Okay, these are some of the 3 points that you can write in this case. Okay, let's move on to question 1.6. Now question 1.6 says that during the titration, the chemist rinsed the inside of the conical flask with deionized water. The water used for rinsing remained in the conical flask. Give one reason why this rinsing can improve the accuracy of the end point of the titration. This is 1 mark, 1 point. You're just going to directly write this line, is that it's going to returns the reagent. It returns the reagent on the sides. Okay, it returns the reagents on the sides of the flask to the reaction mixture. Okay. Next question 1.7. Explain why the water used for rinsing has no effect on the accuracy of the titer. Is because this does not change the number of moles, or the water is not a reagent. So you can mention this point, is that this does not change this does not change the number of moles of reagents. Or you can mention that the water is not a reagent. These are some 2 points that you can write in your exam to score those points. The water is not a reagent. Okay, let's move on to the next question. Whoa, that's a pretty big question. Benzocaine is a useful anesthetic. Benzocaine is an ester that can be prepared by the reaction of 4-aminobenzoic acid with ethanol. So you can see the diagram here shown. how benzocaine is an ester, how it's reacting with, we're seeing the reaction of 4-aminobenzoic acid with ethanol. So you can see it reacting with ethanol in this case. Ethanol, if you name the skeletal formula is 1,2, so that means it's ethanol. There are 2 carbons over there. So this paragraph is at 1.20 grams of 4-aminobenzoic acid. Look at the keywords: excess ethanol, okay, concentrated sulfuric acid, reaction mixture, addition of sodium carbonate, isolation of benzocaine, solid wash with water, recrystallization, and the melting point was determined. Explain why reflux is commonly used to complete organic preparations. So this is for 2 marks. What you're going to write is, you don't need that fluff of data that's given. You can just understand why people use reflux. So what you're going to do is you're going to write that these reactions are slow. You can make out from the paragraph also is because the reaction mixture was then heated under reflux for 45 minutes. So that's quite a long period of time. So you can say that these reactions are slow. Okay, so these reactions are slow as they require covalent bonds to break. We're just gonna write every good point for 2 marks. As they require covalent bonds to be broken. Okay. And this heat speeds up these reactions, these processes in this case, okay? Or you could also mention that many of these organic compounds they are volatile. They're volatile and they have low boiling points. Or you can mention that they boil at low temperatures. I'm just showing you the variations of different points that you guys can write in your exam. Okay? And they boil at low temperatures. You can also mention that reflux, right, allows vapors of volatile organic compounds to return to the reaction mixture. Okay, and this does not allow, or you can mention that reflux does not allow any vapor to escape. Okay, that's one of the points. This is for 2 marks. Okay, let's move on to the next question. Calculate the maximum mass of benzocaine that can be formed by the reaction of 4-aminobenzoic acid. The MR is given to you. Now this is when we're going to be using that fluff of data that is given, actually, because this is a calculation base, so you do need to analyze that. So what I'm going to do is I'm just going to take the main bits of this paragraph. Okay, we're just going to take the main bits of the paragraph. Okay, we're just going to analyze that, crop it, and then paste it. Okay, I'm just going to put the paragraph here just for a moment so that we know what we're looking at, a piece of data. So again, we're going to go to the formulas. Not that book. Formula we're going to be looking at this formula over here, which is very important. Okay, the triangle we have there, and the conversion ratios. Okay. All right, so this is a paragraph. Okay, so now let's answer this 3-marker. Calculate the maximum mass of this formed by the reaction of that 4-amino-benzoic acid. The MR is given to us. So now what do we have to do first? What we have to do is we're going to actually calculate the number of moles of MR of 4-amino-benzoic acid. The reason is because we have given the MR of this. On top of that, we know the mass of 4-amino-benzoic acid. If you look at the paragraph, that's why I brought the paragraph here. If we look at the paragraph here, it's actually 1.20 grams of 4-amino-benzoic acid. So it makes it much more logical to actually calculate the number of moles of amino acid, and we're going of amino-benzoic acid. And from there, we can use that and multiply it by the MR of benzocaine acid, of benzocaine, to calculate the mass. So, okay, let's do the first step. We're going to calculate the number of moles of 4-amino-benzoic acid. So what I'm going to write here is that we know the mass. Okay, we're just claiming that, yeah, we know the mass of 4-amino-benzoic acid to be as 1.20 grams. So that means the number of moles of 4-amino-benzoic acid is going to be, we're going to use a triangle here, mass divided by the MR, which is given to us in the question here as well, 137. So we're going to use a calculator here. In this case, I'm just going to be using that. Okay, 1.20 divided by 137, so it's going to give you a value of 8.759. Some people round it off, but I would prefer you guys write down the full value. Like, actually, it's worth it writing down the full value. If you want to write to at least 4 significant figures, that's also fine. I'm just going to write the whole value here so we can use that and get more accurate values. Okay. Now we know the number of moles of amino-benzoic acid. Is this a 1-to-1 ratio as well? Yep, this is also a 1-to-1 ratio. So that means we can use the number of moles of 4-amino-benzoic acid, and we can consider it as the number of moles of benzocaine acid. Okay. Now we know the number of moles now of benzocaine acid from the number of moles of 4-amino-benzoic acid. We need to multiply that by the MR of benzocaine acid to get the maximum. So I'm going to multiply by the MR of benzocaine to get the maximum mass. Now, how do we know the MR of benzocaine? Is that we look at the diagram. Okay. Remember, benzocaine is an ester. So what we're going to take is we're going to take this diagram of benzocaine. We're going to take this and we're going to find out the number of carbons, the number of oxygens, the number of hydrogens that are attached here. And accordingly, we're going to, now we don't need this paragraph at all. So from this diagram, we're going to make out the MR. Okay, how we're going to do that is, I'm just going to show you. We're going to now calculate the MR of benzocaine. Okay, you're going to use blue pen here, okay? This is 1 oxygen, 2 oxygen, so that means there are 2 oxygens. It's a double bond, so that's an alkene, kind of. Assuming that alkenes are double bonds, right? Yeah. Skeletal formula. These both are connected by carbons over here. So this is 1 carbon, 2 carbon, 3 carbon. This is connected to a carbon over here, which is 1 carbon, 2 carbon, 3, this has a carbon, carbon, carbon. So how many carbons are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 carbons, okay? There are 9 carbons. How many hydrogens are there? If you look at the calculate structure, there's a hydrogen. If we remove the number of carbons over here, right? Okay, let's just put that in green now. The number of hydrogens that are attached here are 1, 2, 3, and 4. Okay? So now we know that that there are 4 hydrogens here. What we can do now is that in total there are 4 hydrogens, so that means we can write that part here. So there are 4 hydrogens. So now we know the number of oxygens, the number of carbons, and the number of hydrogens. There are 2 oxygens, there are 9 carbons, and there are 4 hydrogens. So from the basis of this, we can use again the data insert sheet. If you look at that, we're going to look at the relative atomic mass of oxygen. Oh yeah, by the way, we have to also look at the number of nitrogens. It's actually not 4 hydrogens. Remember, it's 4 plus 2 hydrogens over here. So that means it's 6 hydrogens in total, and there is 1 nitrogen molecule. So we know the relative formula, the relative atomic mass of carbon is 12, nitrogen is 14, oxygen is 16. So we're just gonna take a piece of this, okay, so that we can see clearly what the table is showing. So over here we know the MR of benzocaine is 9 oxygens. So what we're going to do is there are 2 oxygens, 2 times, we're going to write here 2 oxygens, 9 carbons, 6 hydrogens, 1 nitrogen. Okay, now we're going to calculate the MR. We know that there are 2 oxygens, so it's going to be 2 times the relative atomic mass of oxygen plus 9 times the relative atomic mass of carbon plus 6 times the relative atomic mass of hydrogen plus nitrogen, 1 times the relative atomic mass of nitrogen, which is 14. This all should be equivalent to maximum of roughly 9 times 12 plus 6 times 1 plus 1 times 14, which is 165. Sorry, 160 if you add up these whole numbers together. Now, since it's 160, where do you get that 5 additional points? So if you look at the diagram carefully, we need to get 5 more, because the MR of benzocaine is actually 165. So we have to find out where that additional 5 is coming from. So I'm assuming that that additional 5 is actually coming from the, let me just confirm that. 6 times 1 is 1 times 14. So it's not 3 oxygens. So let's just check again. There are 2 oxygens here. There's a carbon, there's a carbon, and there's a carbon. Carbon's there. 1 carbon. Okay, so that's 1, 2, 6 plus 3, which is 9 carbons. The number of hydrogens that are located is 1, 2, 3, 4 plus 2. There are 6 hydrogens. There's only 1 nitrogen. Let's just check this diagram carefully. 1, 2, 3. Okay, if you look carefully, this is actually a methyl group over here. So That means there's the number of hydrogens are a bit different. So it's 4 plus 1 plus 4 plus 2 plus 3. There should actually be about 2 times 16 plus 9 times 12 plus 9 times 1 plus 1 times 14. About 163. This is, remember, this is a methyl group, so that means this is actually, sorry guys, the number of hydrogens here is CH3, and there should be 2 hydrogens over here, so that means it's 4 plus 2 plus 3, which is 9 hydrogens over there. There are 9 hydrogens over there, plus let's look carefully. It should be bonded to 1, 2, 3. Okay. 1, 2. Okay. Maybe 10. Okay, 2 times 16 plus 9 times 12 plus 11 times 1 plus 1 times 14. Yep, there should be 11 hydrogens. Technically, there should be 11 hydrogens here in this case. So if you do 4 plus 2 plus 3 plus 2, which is, 4 plus 2, 11 plus 2 times 16 plus 9 times 12 plus 1 times 14 will give you 165. There should be 11 hydrogens. Okay, be careful with that. Okay, there are going to be 11 hydrogen molecules. So what I'm going to do is, there are 11 hydrogens in this case, not 6. Sorry about that. 11 hydrogens. That's because if you take the 4 green hydrogens, you add it with plus 2 plus 2 plus 3, that will give you 11 in total. Okay? So now we're going to put this in calculation. 2 times 16 plus 9 times 12 plus 11 times 1 plus 1 times 14, which is going to give you 165. That's going to be the MR of benzocaine. Okay, careful with that. Right. Okay, that's going to be our MR of benzocaine. Now we can calculate the mass of the product. Like said earlier, the mass of product is going to be equivalent to this value over here, which is the number of moles of 4-amino-benzoic acid, and we're going to multiply it by the MR of benzocaine, 165, which is going to give you the value of 8.7591088 times. It's going to give you the value of 1.445 grams prox, which we rounded off to 2 decimal places as 1.45 grams. Now, just for clarity, I'm just going to show it to you guys again how we have looked at the carbon structure of benzocaine. There's a carbon over here, there's a carbon over here, there's a carbon here, there's a carbon here, and a carbon there. This is a carbon, this is a carbon. The number of H's that are located here is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 9 plus 2 is 11. So, and the number of carbons is 5 plus 7 carbons. Okay. So, sorry, not 7 carbons. It's actually 1, 2, 3, 5 plus. This is also carbon. Sorry guys. This is a carbon over here. Anywhere else is a carbon. This is also a carbon over here. So it's actually 6 carbons. 6, 7, 8, 9. So there are 9 carbons there, and then there are 11 hydrogens, and there are 2 oxygens, and one nitrogen. Okay. Yep. That's I just shown the diagram so that you guys can clearly see where the hydrogens, nitrogens, carbons, and oxygens are coming from, and how we're calculating the MR of benzocaine. Okay. All right. So just the main reason why the actual mass obtained is less than the maximum mass. You guys can see that when we have seen in this diagram, we can see that there's a reversible sign over here. Now this is really critical to answer the question of why the actual mass obtained is less than the maximum mass. So what we're going to write is, we can write that the reaction is reversible, meaning that the forward and backward reactions are equivalent to each other. So that means the reaction is, that is when it's in equilibrium, by the way. The reaction is reversible. That means the reaction is in equilibrium. You can mention that as well. Is in equilibrium. Okay. Next question. Identify the gas evolved when the aqueous sodium carbonate is added, and explain why this gas is evolved during the stage of the procedure. When there's aqueous sodium carbonate added, that means there is carbonate ions, CO3 minus ions being present. So that means carbon dioxide gas is going to be there. Carbon dioxide gas, or you can mention CO2 gas, is the identity of that gas. And the explanation for that is that the sodium carbonate slash the carbonate ions. Okay, it's going to write that properly. Slash the carbonate ions. They react with the sulfuric acid catalyst, or you can mention that the unreacted 4-amino benzoic acid. Okay. Explain why benzocaine is washed with water. The obvious reason is to remove sodium sulfate. You can also mention that it's used to also remove unreacted sodium carbonate solution. Okay. Next question. The benzoic was recrystallized, purified. Outline the method that should be used to recrystallize the benzocaine. Now this is for 4 marks. You have to just memorize some of these steps. You're gonna dissolve the benzocaine in the minimum volume. That minimum volume is a really critical keyword, and you're going to use a minimum volume of water, or you can mention the word solvent. On top of that, you're going to use hot water, or solvent can also be mentioned. You're going to allow the solution to cool. You're going to allow the solution, just going to show the question there. You're going to allow the solution to cool and crystals to form. Okay. On top of that, you're going to filter off the pure product. Under reduced pressure under reduced pressure, and you're going to be using a Buchner funnel. By the way, you guys can research up what a Buchner funnel is. By the way, it's just some kind of diagram that kind of like looks like a Buchner flask, and there's a vacuum pump over there. There's some, I think there's some Buchner funnel placed in there, so the diagram kind of looks like that. But yeah, do search that out what a Buchner funnel is to check it out. You can use a Buchner funnel and a side arm flask. Okay, so you can use using a Buchner funnel and a side arm flask. Purity of the product can be determined by measuring the melting point. State 2 observations about the melting point that indicates that it's pure. So if it's pure, that means it will melt sharply. That's one keyword, that it melts sharply. Okay. On top of that, you can also write that it agrees with the data book. It agrees with the data book value. Okay, there must be a preservation of some of these values there.